Good morning, everybody. Welcome to day 3 of the AFLOW school. My name is Cormac Toher, and today I'm going to be talking about how we can calculate thermal and mechanical properties of materials using the AFLOW-AEL and AFLOW-AGL. So this is the automatic elasticity library and automatic Gibbs library for thermal and mechanical properties. Okay. So I'll start off with, why are we interested in things like thermal and mechanical properties of materials? So what kind of applications are important? Are these types of properties important for? So in the top left here, you can see we have, these are the properties for where we have specific mechanical properties, especially things like super hard materials and wear resistant coatings. So these tend to be used in machine tools. So things like cutting blades, drill bits, various other tools for machining materials. For both thermal and mechanical properties, what materials that are mechanically strong but also have good are thermally insulating tend to be used as thermal and environmental protection barriers for things like turbine blades inside jet engines, gas turbine engines, etc. So the idea of this is that you have a coating here that's both oxidation resistant, so it's going to be resistant from attack either by the hot air coming in or by the combustion products. But it's also going to be thermally insulating, so that it protects the underlying turbine blade, stops it from getting too hot. And it's also going to be reasonably mechanically strong, so it's not just going to fall apart. So it's quite difficult to get a material with these combinations of properties. So another example would be something where you might want high thermal conductivity, will be heat sinks for advanced electronics. So if you want to put something that's going to conduct away you might want something that's an electrical insulator, but something that's a thermal conductor. So you have something that's a so it has a reasonably large band gap, but has high lattice thermal conductivity, so it will transport heat away from your electronics. And also you might want something with high heat capacity as well, it doesn't heat up too quickly. So in order to calculate these types of properties, to calculate elastic properties, the way we do this is we apply a set, we take our unit cell of our material, so like before, like you were generating for the postcards, and you apply a set of normal and shear strains. So normal strains, you basically just stretch it like this in one direction. A shear strain, you do something like this to it. So what we do is we apply 4 strains in each independent direction. So you've got 2 that are expansion strains, so 2 where you stretch it out, and then 2 where you compress it inwards. Then the maximum applied strain, or at least by the default, is 1%. I'll show you how you can adjust this inside the files. So by applying these strains, then we can calculate, so for each strain structure, we calculate the stress tensor. So what we do, we have these correspond to the different strains. So each one of these is a specific strain, and this is the resultant stress tensor for each strain. So for example, if we apply this strain, so this is along the x direction, so a tensile strain in the x direction, we calculate this full stress tensor, and then by basically saying, okay, you're hitting this stress strain relationship down here, so this component of the stress tensor is going to be equal to this component of the this elastic constant times this component of the strain. So you know the strain because that's what you apply. You calculate the stress, and then therefore you can solve this equation to calculate the elastic constant. In our case, we have multiple of these strains, multiple of these stresses, and then we basically fit this stress strain curve, so we get an average. And this is to allow for the fact that you might have some noise. For example, if the stresses are too small or too large. So if they're too small, you might have some numerical noise. If they're too large, you might start going outside of the linear elastic relationship. So this allows you to check to make sure to actually get these elastic constants. So you get this average value, so you get this reasonably robust result. Then you do this for each one of these strains, and this gives you this full 6x6 elastic tensor. So this is known as the elastic stiffness tensor. The individual components are known as the elastic constants. So this is and then you have what's called the compliance tensor, which you get by inverting this. So that basically, the compliance tensor really tells you what the strain response will be for a particular stress. So this tells you what for a particular strain, what the stress response will be, but usually in actual practice, you apply when you're actually doing experiments, you apply stress, and you want to know what the strain would be, how much the material is going to perform for a particular applied stress. And from that you can get from this compliance tensor, which is the inverse of this. Okay, so once we have these elastic constants, then we can go and calculate things like the bulk and the shear modulus. So there's a couple of different elastic, a couple of different approximations you can use. One is in the limit of assuming that the strain is isotropic. So this is for polycrystalline materials. So you assume that you can either assume that the strain is constant across the materials or the stress is constant across materials. And this gives you the Voigt approximation, which is sort of an upper bound for the bulk modulus, and the Royce approximation, which is a lower bound. So these components here, these are just your standard elastic constants. And from that, you can calculate the Voigt approximation, the bulk modulus. And then the Royce approximation is determined from these components, which are the components of the compliance tensor, which are the inverse of this elastic constants, as mentioned before. You do a similar thing for the shear modulus. So you have the Voigt and Royce approximations. And then we can do what we call this VRH average. So this is from Hill. You have this Voigt, Royce, Hill average, which is basically just the mean of the two, of the Voigt and the Royce approximation. And this is usually a reasonably good estimate of the bulk modulus and shear modulus of the actual material, polycrystalline material. And these are usually the values, if we want to take sort of when people ask us which of these bulk modulus should we use, we usually recommend to use this VRH value. And then once you have these bulk and shear moduli, we can also estimate things like the Poisson ratio from this expression here. And this is sort of a measure of if you stretch the material in one direction, how much does it compress in the other directions? In directions perpendicular to the applied stress. Okay, so that's how we do the elastic properties. So these are these zero temperature elastic properties. Now we want to talk about how we can calculate thermal properties. So to do this, so there's several different levels at which we can calculate thermal properties. So the method I'm going to show here is sort of the simplest one we've implemented in AFL, sort of the least computationally expensive. Tomorrow, Dr. Marco Westers and Dr. Andriy Smolyanyuk will be talking about how to calculate the phonons, either in the harmonic approximation or the quasi-harmonic approximation. So in this case, what we have here is what's called a quasi-harmonic Debye-Gruneisen model. So we start from our standard size unit cell, and then we apply a set of isotropic compressive and expansive strains. So this we get sort of energy. So we calculate for each one of these different volume structures, the different volume unit cells, we calculate the energy. So we get this energy as a function of volume curve. We can then fit this by an equation of state or by a polynomial. And from this, you can get things like the bulk modulus. So this is, if you're fitting it by a polynomial, this is the expression. You have other equations of state you can use, such as the Birch-Murnaghan equation of state. So this gives you the bulk modulus as a function of volume. From this, you can calculate the Debye temperature as a function of volume using this expression, where this is the bulk modulus. And this here is a function of the Poisson ratio, which we get from AEL, as I discussed in the previous slides. Then from this, you can calculate the Helmholtz vibrational free energy. So this is the vibrational contribution to the free energy from this expression here. Again, as a function of, this will be as a function of volume and as a function of temperature. Then for each volume, so for each pressure and temperature point, we calculate the full Gibbs free energy. So if you have the energy as a function of volume we get from DFT, you have this vibrational contribution that we get from this Debye model, and then we have this pressure volume term. So we can also calculate as a function of both pressure and temperature. So for each pressure temperature point, we have this Gibbs free energy as a function of volume. Again, we can fit this by a polynomial, and we find that the equilibrium by finding the minimum of this Gibbs free energy as a function of volume for a given pressure temperature point. We find the equilibrium volume for that pressure and temperature point, and that then gives us that gives the equilibrium volume for that pressure and temperature. Then you can calculate the Debye temperature, the Gibbs, the vibrational free energy, the bulk modulus at that pressure and temperature. So once we have the Dubai temperature, we can also then calculate the Grunizen parameter, and Andrea is going to talk a bit more about this tomorrow. But it's basically a measure of how things like how the thermal properties, things like the Dubai temperature, photon frequencies vary as a function of volume. And as such, it's a measure of the anharmonicity of the crystal. So if you have a perfectly harmonic crystal, then this energy volume relationship will be a parabola, perfectly parabolic, which means that the second derivative will be constant. And because the Dubai temperature is proportional to the bulk modulus, that means the bulk modulus as a function of volume will be a constant. And all these thermal properties will be constant with respect to volume. But the Grunizen parameter then is a measure of how this deviates from this anharmonicity, this perfectly parabolic energy volume relationship. Then we have another thing that's called the acoustic Dubai temperature. So this is sort of an approximation, and it basically tells you what is the Dubai temperature if you only include the acoustic modes of the crystal. So Marco is going to talk about this tomorrow morning a bit more, about the difference between acoustic modes and optical modes. But these are basically the lowest frequency vibrational modes. And these are the ones that are most important for thermal transport. So from this, you have this expression that's developed over a few years. As the original was what was called the Liebfried-Schliemann model. Then you had a Slack built up developed this type of an equation of this form from it. So this gives you using this Dubai temperature and the Grunizen parameter and a few other things like the mass, the volume, and etc. You can estimate the Gibbs free energy, the lattice thermal conductivity at the acoustic Dubai temperature. And then you can sort of use this 1/T assumption of the behavior of the thermal transport to estimate what it is at other temperatures. Okay, so how well does this method work? So here's on the left, we have the Dubai temperature. So this, on the y-axis, we have the calculations. On the x-axis, we have the experimental results extracted from literature. So this for a set of different types of structures. So you've got zinc blende diamond type structures and the blue circles. Green squares are rock salt, and the purple pluses are wurtzite. So as you can see from this plot, there's actually quite a good linear relationship between the values we get from our calculations from this AGL model and the experimental values. On this side, we have the thermal conductivity. Here you can see again, our calculations are on the y-axis, while the experimental results from the literature are on the x-axis. And you can see here the agreement isn't quite as good. We still get but at least we get the trend more or less correct. So the reason for this is that while the Dubai temperature is pretty accurate, the Grunizen parameter tends to be overestimated using this model, which means that because the Dubai temperature, because the Grunizen parameter is in the denominator, that means that the thermal conductivity tends to be underestimated. So you can see here that while it does tend to be underestimated, the general trend in most cases is reasonably good. So this means that while might not give you quantitatively accurate results, it is useful for rapid screening of thermal properties. So if you want to build up a database to do things like training machine learning models or do rapid screening to identify materials for more in-depth computational investigation or experimental investigation, it's quite useful for these types of applications. Okay. So we have combined this workflow, so whereby we run AEL, then we use the Poisson ratio from AEL in the AGL calculations, and it's one sort of integrated workflow within AFLOW. It's been run for over 6,000 materials now. The database is accessible at aflow.org by the REST API and AFLUX that Dr. Esther showed you yesterday. So the keywords are things like AEL bulk modulus AEL_bulk modulus_VRH, which we were using, for example, yesterday in some of the exercises. We also have things like the shear modulus, the Poisson ratio, and so on. Similarly, you have thermal properties keywords for the Dubai temperature, Grunizen parameter, heat capacity, thermal conductivity, thermal expansion, etc. So we can also generate a, so I'm going to switch now to the 3D desktop terminal. I'll show you how, start showing you how this works in practice. So you can generate an AEL, an AFLOW.in file with AEL switched on by just appending this. So for example, this is the prototype. So this is the command to generate an AFLOW.in file using a specific prototype. So Dr. Hicks was showing you this yesterday. Minus module equals AEL. We'll switch on the AEL workflow, and minus module AGL will switch on the AGL workflow. And you can also then edit this .aflow.orc file to start changing these parameters. I'll talk to you a bit more about this in the next few slides. But first, let me show you how this actually works in practice. Okay, so let me go to my desktop terminal. So I'm going to go into this 06 AEL AGL, and I'll just generate them here for the example. So I use AFLOW minus AFLOW underscore proto equals AB underscore. Okay, my desktop seems like that. Okay, so there's a question in the chat. He says that theoretical estimates of conductivity should normally underestimate, as we often can't. Okay, so I think, no, this is, so that if you look at this, this method is actually underestimated. So the experimental value is here. Theoretical value is here. So we're actually underestimating the conductivity. So usually, okay, what you're arguing is that, so it's true if you're actually trying to calculate the different scattering mechanisms, you will tend to have a thermal conductivity that's too high because you haven't included higher order photon scattering mechanisms. In this case, we're not directly trying to calculate the scattering mechanism, the individual scattering events. So at this level, you tend to calculate, you're trying to just estimate what the scattering events would be from the anharmonicity of the energy volume curve. So it kind of integrates all the scattering mechanisms, and it actually tends to result in an overestimate. Now, this is probably, there's a few different possible reasons why this could be. So first of all, this method itself is very much approximate. So even the model itself is kind of an approximation. The other value is that these are at 300 Kelvin, but as you showed, this 1/T is not necessarily also an accurate model for how the thermal properties will vary as a function of temperature. The other reason is that another possibility is that we're using the PBE exchange correlation functional. This tends to underbind, so it tends to make the bonding too weak. And that in turn will tend to result in an underestimate of things like the thermal conductivity as well. So it tends to underestimate, you'll see that the bulk modulus is underestimated, various other quantities are underestimated, and in particular at longer distances, it will tend to underestimate even more, which will probably make it look, the energy volume curve look more anharmonic than it otherwise would be. Okay.
Just to add a little bit to that, if you don't include all scattering mechanisms, you actually overestimate your thermal conductivity too. For example, boron arsenide has a lot of 4-photon thermal conductivity, 4-photon scattering. So if you only include 3-photon scatterings, you get a huge thermal conductivity, but the actual experimental values are going to be much lower. So if you don't include all scattering mechanisms, because scattering reduces thermal conductivity, you will actually go to an overestimation of the thermal conductivity, not an underestimation.
Yeah. Okay. This is stuff. Okay, so first I'm just going to generate this without using the module AFLOW commands. So this creates an AFLOW data directory, which we can go inside. Then we can, let's cap this so we can look. And here we can see we have this AFLOW_AGL calc and AFLOW_AEL calc. So both of these are now commented out. So this won't run either AGL or AEL. So if we go back, let's delete this one and do the same thing again, but this time with the AEL module. Okay. Okay, looks like my terminal is a bit slow this morning. Okay, anyway, while we're waiting for this to go through, let's go back to the slides. Okay, so here I mentioned before, we have this AFLOW_AEL calc line. We can then determine the number and size of shear strains. So
there's a question in the chat.
Okay, can we turn on both modules at the same time? I haven't tried this. What will happen is that you might turn on both modules, but what's going to happen is that AFLOW is only going to run one of them when you actually run the calculation. And AFLOW reads the AFLOW in file from the bottom. So whichever one is lower down in the AFLOW in file, it'll run that one first. That will take the priority. So let's see if we actually, what actually happens if we do both of these. Let me exit out of this. Yeah, so I think the version that's inside the PDF was probably a bit out of date, but let's try with, let me try running this question that was asked. Okay, this is running a little slow. It's still running slow. Okay. Okay. Yeah. So so this previous slide was added, I think, a bit late, so it might not have made it into the version that's actually on the desktop. But we'll try and see if we can get that replaced for you before the end of the day. Okay, here we go. So let's try with both. The person asked them the question. Let's see what happens. Okay. So in this case, oh, it didn't read either of them. Okay. So yeah, so the answer is no, you can't turn both on at the same time. Yeah, it's not something we've ever tried to do. Let me see if I can do what's one of them to show an example if this desktop works. So, and the thing is, if you did uncomment them both by hand, like I said, what we'd do is it would run them in reverse order. So it would run them from the bottom first. Okay, so let's just do just AEL. Now let's see. Yeah, now you can see that the AEL, AFLOW_AEL calc is uncommented inside. Okay, let's go back to the slides. Okay, so if this line is included and uncommented, then the AFLOW-AEL workflow will be run. So as I mentioned before, we apply a number of normal and shear strains. So you can, this is something that you can change inside the AFLOW file. You can also change the default values that are used by editing your AFLOW-RC file. You can also change the size of the strain step and the size of the shear strain step. This is something that you might want to do if you have a very hard or very soft material, particularly for very soft materials where you might need to apply larger strains so that you're not to actually overcome numerical noise. So you have to have a large enough stress that you actually can, that you get a reasonably reliable stress value. Because if the stress value is very small, the error in the stress calculation might be of the same magnitude as the actual result. So it might not be reliable. We also have included we can use symmetry to reduce the number of independent directions. So for example, in a cubic cell, this direction, and this direction should all essentially be the same. So in this case, if we use the AFLOW sim that David was talking about yesterday, it checks what the symmetry of the system is. If it sees that it's cubic symmetry, it says, oh, we only need to do one of these strain directions. We don't need to do all three. And this reduces the number of calculations we have to do by a factor of 3. Okay, and then we can run the DFT calculations for all of these strain structures just using one command, using this minus multi option. So this will go and turn into each directory in turn inside this. So each subdirectory that's inside your main directory that you run this in, and it will actually calculate each one in turn. So you don't need to run all the VAST calculations separately. Okay. So now, yeah, let's try some exercises. So we're going with a few exercises here. So first one is that we make a cut is to go into this 06_AEL, it's like AGL_AEL directory, and then comment the appropriate line to run an AEL calculation, and also rename the lock file. So then use this command to generate the subdirectories for this AEL calculation and see how many subdirectories are created. Then we make another copy, and we change then to switch the option to control the number of independent directions to off. And rerun this and then see how many directories are created now. And then finally, in this new directory, so this is the one that's where it's already AGL have already been run, and we're going to try doing the post-processing. So we have the VAST calculations run, but now we need to do post-processing. So we run this command here, and then you find the values of the bulk and shear moduli and the Poisson ratio in this file, aflow.ael.irish. So let me briefly just show you where we need to go before we break up into the breakout rooms. So if we go into this exercises directory, go into AEL. Okay, so here's here's the results of a DFT, of an AFLOW calculation that have already been run. And what we're going to do here is actually run the AEL calculations on top of these DFT calculations. So let's say you did a relaxation, you calculated the band structure, the density of states, and now you want to go back and calculate the you want to go back in and you want to calculate the elastic properties. So what you can do is you go to this AFLOW.in file. You go to AFLOW.AEL, you would delete this comment. That's the first thing you need to do. Then you need to, this lock file here will prevent anything else from being run in this directory while it's present. So you can either best thing to do is to rename this file, call it something like lock.orig or something like this, or lock.run or doc. Whatever. And then you can rerun the calculation on top of this. And then you would, in this case, we just run the command, use this command aflow -run equals 1. This will just create the subdirectories because we don't want to run all the VASP calculations because that would actually take quite a long time because there's going to be like about maybe 8 different VASP calculations that we need to run. Okay. So now if we want to split up into our breakout rooms, so we can actually, you can actually try these exercises yourselves. So do we want to put people into breakout rooms?
So let me go ahead and make breakout rooms. So 5 rooms.
And I think for this, if we take about 15 minutes, so, well, it's 9:40 now, Central Time. So if we meet back here at, let's say 9:55 Central Time by the time we're all in our breakout rooms.
Mark, are you making them?
Yep.
Okay.
Okay. It should be open now.
Okay, so let's just go into our breakout rooms. People are coming back. So we'll just go through this exercise quite quickly. So here I've already renamed my lock file. So let me go into my aflow.in file. And I undelete this and comment this.
Cormac, want to share your screen?
Oh, sorry, sure. Share. Okay. So I've already renamed my lock file. So if I go into my the AFLOW-in file, I uncomment the AEL calc. And then I can run. And this will run all of the, generate all the files. Okay, so here we can see we have 8 files. Let me just rename the lock file that we have. And now we're going to change this strain symmetry to off. So now it doesn't check if it's cubic anymore, and instead it applies the full set of normal and shear strains. But now you can see it's generating a lot more different strains. And it's writing a lot more different directories. Okay. So now if we go into this one, okay, let me not here. So I've already run this post-processing. So now we'll look at this output file, this AFLOW.AEL.out. So do AXCcat, AFLOW.AEL. So here we can see the results. So here we have our Poisson ratio, we have our shear modulus, so the Voigt and Royce approximations, then we have the VRH average values. Then you have other things like the Young's modulus, speed of sound, etc. And down here you have the stiffness tensor. So these are the individual elastic constants. You can see because we have this cubic symmetry, these values are all the same. So in each, so this is in the X direction, essentially X, Y, Z directions. They're all the same, which you'd expect for cubic symmetry. And here we have, these are C12, these values are C12 and C13 and C23 are all the same as well. And then these shear elastic constants are the same as well. Okay, let me just see if I can scroll up a little bit. I'll show you the actual. No, it doesn't go like that. Okay, so let's move on to the AGL part. Okay, so again, its method is quite similar to AEL in terms of what you actually have to do. You have, again, this AGL calc line. If you uncomment this line, then it will run an AGL calculation. You can also control the number of, and the number of the different size volumes that you can do. You can change the strain step size. So again, you can either change these in the AFLOW.in file for a particular calculation, or if you want to train the default values, you can edit your AFLOW-RC file. You can also set the Poisson ratio that you use using this line, or you can take it from AEL. So this is usually the default is what we do, is we use AEL to calculate this Poisson ratio that's used in this AGL part. You can also run the DFT calculations for all the strain structures that are generated, again, using the AFLOW - multi command. So again, now we're going to do some exercises for this part. Again, we want to make this, we want to uncomment the appropriate line to run an AGL calculation and rename the lock file, and then use this command to generate the subdirectories. And then see which subdirectories are created. So now we want to do, the next one will be we do the same thing again, but this time the AEL option to calculate the Poisson ratio is switched to off. And then we see how many subdirectories are calculated. And then finally, we go into this other directory and we run the post-processing. And then we look inside to see what are the values of the lattice temperature and the lattice thermal conductivity from this file. So lattice thermal conductivity, in this case, use the value of 300K that's at the top of this file. Okay, so let me just show you where these directories are before we go into the breakout rooms. Okay, so here's our MGO directory. It's inside this AGL. Here's our, so again, we do something like move the lock file, change the name of the lock file. Got a reach here. Load that in. In this case, we would uncomment this line, and then we would try running. Okay, so with that, let's go back into our breakout rooms. Let's do about 15 minutes again. So we meet back at 10:20 Central Time. So I think our breakout rooms already set up.
Yes, I think
The same ones.
Yeah, they're already people going back in. Okay, So let's go back to it. Okay, so just to run through these exercises very quickly, here's the aflow.in file. So the first one to do is we uncomment this, save, and then we run. And here you can see this, even though we uncommented the AGL line, it's creating the A1, the AEL A runs. Okay, so the reason for this is that we have this one switched on, AEL Poisson ratio switched on. So what happens is then the AGL, it sees it has to run, but it also sees that it wants the AEL Poisson ratio. So first it's going to check if AEL has already been run in this directory. And if not, it's going to set up the AEL files and start running them first, because it needs that to do that first to get the Poisson ratio. So if we switch this off, so we don't use the Poisson ratio, and now it's going to use a default value, which is going to be 0.25, unless you set something different in by hand. So we save this. I'll just delete these other ones. Don't necessarily need to do that. But then I run it again. And now you can see it's creating the AGL input files. Okay. And now you see with 28 of these AGL input files. So if now we go to the other directory. So here we've already run the calculations. We both have AEL calculations run and we have AGL calculations run. So we have the DFT calculations all run. So now we're just going to do the post-processing. And so I've already run this. Again, it will just be the same command. But again, you have to just make sure you move the lock file. And now we look inside, you can see we have both the AEL output files and the AGL output files. Because we have the AEL switched on, it's going to run both workflow, AEL Poisson ratio switched on. We just want to run both workflows and print out the results for both workflows. So if we look inside this AGL.out file, I'm going to open it with VI just because it's a long file and it's zipped. So if I go back up to the top, so here we have the main results. So here's the thermal conductivity of 300K, the by temperature, and so on, Grunizen parameter, and so on. Here we can get the same properties, these thermal properties as a function of temperature. So things like the heat capacity, constant volume, and constant pressure, thermal coefficient expansion, etc. And then down below here, we have the energies as a function of temperature. So this is these sort of thermodynamic quantities. So here we have a Gibbs free energy, a vibrational free energy, vibrational entropy, and so on, the internal vibrational energy, etc. Okay, so that's the AGL output files. So that's the end of this session. So if anybody has any questions before we wrap up, otherwise we can go and take our break.
Hey, Cormac, could you explain why the using a Poisson ratio of 0.25 is an okay a default?
Okay, so that's what's called the I think it's the Cauchy ratio. So this is sort of the what you would expect from an ideal material. That's if it's only deforming elastically and it's sort of maintaining constant volume, basically, you would expect that if you stretch it in one direction, it's going to go in a certain amount in each of the other directions. It's going to go like maybe down by a quarter in each of the other two directions, and that tells you that. So it's sort of like it would be like the equivalent of a material that conserves its volume when it's stretched.
Okay.
And so that's sort of it's roughly in the middle of the range. Most materials have a Poisson ratio between 0.2 and 0.3.
Yeah.
There's a few ones that have Poisson ratios that are more higher or lower, but usually most materials, pretty much all material, I'll put it this way, all stable materials will have a Poisson ratio of less than 0.5 and more than -1. The materials with a Poisson ratio between -1 and 0 are quite rare. They're sort of unusual materials. So pretty much all normal materials will be between 0 and 0.5, and most materials will be between 0.2 and 0.3. So 0.25 is usually a reasonable approximation for most materials.
Okay, great. Thank you.